Hi everyone, my name is Antoine Grenier and I'm gonna present you Are We Forgetting About Compositional Optimizers in Bayesian Optimization. Let me first introduce the black box maximization problem. So in this problem, f is a black box function. So it is a function that is not known analytically and that is expensive to evaluate. Therefore, we need a sample efficient solution to find its maximum. And that's what provides the Bayesian optimization framework. This framework consists in first gathering initial data from randomly sampled X points that are evaluated. And then after this step, we repeat the three following steps, which consists in fitting a surrogate model on the already observed points, on maximizing an acquisition function, and on evaluating the black box at the point found during the maximization of the acquisition function. So let's first rapidly have a look at the fit of the surrogate model. Usually in BO, what we use is a Gaussian process. So to illustrate how a Gaussian process behaves, we have this 1D example where the black box function is shown in blue. And so we suppose in this example that we have observed only 3 points here that are marked as a cross. And so the Gaussian process will be able to compute the posterior distribution at any point of the third space, conditioned on the already observed points. And so this posterior distribution will be a Gaussian with a mean and a variance that are functions of the x. And so given this model, the next step consists in maximizing an acquisition function. So we have the model here, and we have an acquisition function there. And so an acquisition function alpha is a function that takes as input a set of points x from the search space, and that associate to this set of points a value that corresponds to the advantage we would have in acquiring or evaluating these points with the real black box. And so this acquisition function alpha will trade off the mean prediction and the model uncertainty to suggest the next batch of points to evaluate. We see on this example that where the model has low mean and low uncertainty, the acquisition function is low because it's not interesting to get to query points in that region. When the mean increases, the acquisition function also increases, but also where in the region where the uncertainty is large, it is interesting to get new points, to evaluate points in this region. And the question is now, how can we maximize this acquisition function efficiently? That is the main focus of our paper. And so there are 4 widely used acquisition functions that we will lean on during this presentation. So there is expected improvement, probability of improvement, simple regret, and upper confidence bound. The formula for all these acquisition functions are quite similar in their structure. They all depend on the expected value over the posterior of the GP. And so since they share the same structure, let's have a closer look at expected improvement, and we will be able to extend, we could extend the results we will derive on expected improvement to the other acquisition functions. So the expected improvement takes as input a set of Q points from the search space, which are the points that we would like to acquire. At least that's this set of points we would acquire is the result of the acquisition function optimization, maximization. And so it is expressed as the expected value over the posterior GP prediction given the past observations DI. And what is inside the expected value is simply what the improvement we can get by evaluating the black box at this set of q points x1 to q, because we take this difference between f of x1 to q and the best observed value so far. The problem here is that this acquisition function is intractable in its when q is greater than 1. And so what we can do is to take Monte Carlo approximation. But for Monte Carlo approximation, we see that we would need to sample from this Gaussian posterior. The problem is that the Gaussian posterior depends on the variables we want to optimize on. So it depends on x1 to q. So the reparameterization trick allows to disentangle the sampling procedure from the variables we optimize on. And so this will allow to compute gradients through the sampling, and it will open the door to first and second order optimization. We can rewrite the acquisition function expected improvement using this reparameterization trick. And so the expected value will now depend on a Gaussian that is centered on standard and that does not depend on x. Given this reparameterization formulation, what we can do is follow the empirical risk maximization procedure. So at each step of the acquisition function optimization, we could sample new z's to get an approximation of the acquisition function. But what we could also do is consider the acquisition function maximization problem as a finite sum maximization problem. To do so, we can sample the z upfront and transform the expected value of a z by a finite sum, which of course leads to an approximation. And so from this finite sum maximization, what is interesting is that we show we can derive a compositional form that is amenable to compositional optimization. I won't go through all the steps of the derivation, but what we can see is that starting from this reparameterized FSM form, we can arrive at a compositional form of this shape. So the problem would become a maximization over x of f of the expected value over a random variable omega of g of omega of x. And so, as I said, I won't go through this, but what we see is that we get the same formulation here, and we have this nested form that we can optimize using compositional optimizers. So all this leads to a variety of ways of maximizing the acquisition function. If we consider zeros first order or second order optimization, or ERM or FSM forms, we have, for instance, evolutionary methods or compositional evolutionary methods. We have standard first order optimization like ADAM, ADAGRAD, and so on, but we can also use compositional optimizers such as CADAM or NASA. But we can also use second order optimizers such as LBFGSB or the compositional forms that we introduced in our paper, CLBFGSB. And so now what we would like to do is to assess which one is better, is the best. To do so, we ran almost 4,000 experiments, BO experiments. So we optimized black box functions using BO, but with different acquisition function optimizers. And we observed which value is attained when using each of these acquisition function optimization. The black boxes comes from synthetic black boxes, but also from hyperparameter tuning tasks. And so, interestingly, what we learn from these experiments is that the compositional form, and notably first order compositional solvers, lead to better performance than their non-compositional counterparts. As we see on this left graph, the lowest regret is attained by the first-order compositional solvers, optimizers, and also on the hyperparameter tuning tasks. A majority of tasks are attain a better score when a compositional optimizer is used, which should encourage the exploration of this compositional form in future work. Thank you very much.